Okay, sorry for the mistake, but
no problem.
okay.
You're here, so
Yeah, thank you. Okay, so welcome back for this for this second session of the day. So the first talk will be given by Xiaopan Zhang. Sorry, obviously I'm not able to.
Yeah, just call me Tom. It'll be okay.
Okay, thank you. You say it better than I do.
Yeah.
And it's
difficult.
a common work with Julia Bennell.
Yeah.
Okay, so you've got 20 minutes.
Okay, thank you. May I start?
Oh, yeah, please.
Yeah. Okay. 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 Can you hear me? Is it okay for the phone?
Yes, it's perfect.
Okay. Okay. Thank you. Hello everyone. I'm very glad to introduce the work with Julia when I visited Leeds University in 2019. This problem combines packing and scheduling recept from the shipping transport management of the Three Gorges project in China. And my introduction will follow this outlines. Three Gorges, also known as Shansha in Chinese, is extremely beautiful segment in the upper middle river of Yangtze River. It was very important in Chinese culture, but now has been a critical pivot in electricity network and inland river transport network of China. Because of the Three Gorges project, one of the largest hydroelectric engineering all over the world. Actually, the Three Gorges project is made up of two dams. The Three Gorges Dam, briefly called the TG Dam, and its downstream partner, the Gezhouba Dam, and briefly called GZB Dam. There are total the 6 passageways for vessels to traverse the dams. And let's look at the passageways in the TG Dam, in the Three Gorges Dam. There are two five-tire ship locks and a ship lifter. The locks run batch service, and the ship lifter runs single vessel service. According to the location, the two locks are called the source lock and the south lock. Now, while the Gezhouba Dam is much smaller, with 3 single tire shape locks identified as number 1, number 2, and number 3, in which the lock number 3 is about quarter in size. Generally speaking, the lockage scheduling is to determine the start time and the running directions of each service for each lock, along with the vessel's berth layout in chamber. It's very similar to job scheduling, combining with beam packing, in which the locks act as machines and the vessels are jobs to be handled. Due to their location, a normal vessel just takes about 2 hours to navigate from one dam to another if no stop. So regarding the lockage scheduling needs to cover 6 to 18 hours. The lockage scheduling through the two dams should be conducted in a systematic way. This picture also shows the different running ways of this lock. The source and the north and the south lock in the Three Gorges Dam serve for just a one-way lockage parallelly, whereas the three locks in the Gezhouba Dam run two-way lockage coordinately. So far, we have got three main contributors to this problem. Number one, we built the sequence-based model. And number two, we designed VND, the variable neighborhood descent-based algorithm. And number three, we proposed the rolling horizon algorithm for the dynamic situation. And I'm motivated by the fact that the sequence optimization models have been widely used in both job scheduling and the bin packing problems. We have built the sequence-based model for our problem. Firstly, the vessels applied for lockage should be grouped initially into 5 sequences corresponding to the 5 locks, following the simple first come first serve rule. And the sequence for each lock of the 3 Gorges dam is isolated to or other sequence because they run one-way lockage. And the sequences for the locks in the Gezhouba dam can exchange vessels among them because the locks run two-way lockage, but they are isolated to the sequences for the 3 Gorges dam. And if we have been given a sequence, the lockage surface of its corresponding lock can be generated by the process called serving the sequence. The result of serving a sequence, including setting the surface trigger vessels and computing the surface start time and arranging the berth layout in chamber for their service batch. And the service trigger is the key element in the sequence. They are the vessels that indicate to generate new services. And a service batch of a trigger are the vessels segment from the trigger through all the successive non-trigger vessels behind it. And the vessels in the batch, in the same batch, will be served together. And we also have some constraints to form a service batch. Number one, they must move in the same direction. And number two, they must arrive not later than the service trigger start to be served. And number three, they can be contained into the corresponding locks chamber. So as it's very similar to the bin packing problem, we proposed a procedure based on next feed non-rotational rectangular bin packing to generate the serving of paper, serving the sequence. But we have combined with just-in-time and the direction compatible conditions in this procedure. We just skip over the details of the algorithm, and the main idea of the algorithm is that we just test a vessel could be placed in an open service. If not, there will be it will be set to a new service trigger. But when we check the available, not only by the exceeding the chamber space, but also considering the same direction with the vessels in the open surface, and it should be arrived before the service started. And I think that there are another important conception is the arrival dependencies among sequences. because most of the vessels will apply for traversing 2 dams within the scheduling term. Thus, they will have 2 stages of their routes, but in our model, 2 stages will be treated as 2 individual vessels. So the arrival dependency should be put in between them, just as shown in this picture. And what's more important is that the arrival dependencies require the sequence optimization process to be done sequentially. Precisely speaking, the sequence of the source log of the south log should be handled firstly. Then the arrival time of every vessel in the sequences of the GZB dam can be predicted. These sequences could be optimized together secondly. Finally, the sequence of the north log is available again. So the optimization is guided by the sequence evaluation. Generally, we have 2 aspects of consideration. That the temporal aspect is evaluated by function of total priority waiting time of all vessels, and the spatial aspect is evaluated by the chamber usage caused by this sequence. But as it has been noticed that the raw utilization function ZU is not efficient in sequential bin packing optimization. And so we have introduced 3 more guiding evaluation. And in which the last one, the ZG, is designed by us firstly here. After combining the 2 aspects of evaluation use compound function EW, the model of the GZB lockage scheduling is finally written like that. Thus, the optimal sequence are found by variable neighborhood descent based search process here. As for mentioned, the initial solution is set by serving the 5 first come first serve ordered sequences, and then 4 kinds of neighborhood structure are designed to search in the solution space. They have been shown above in the table. Obviously, it's including moving vessels or surface batch to another sequence, or swapping vessel or surface batch with another sequence, or the original sequence and the target sequence could be as the same one, just for the south log or the north log of the 3 Gorges dam situation. And after disturbed, this sequence should be reserved again, and the other sequence haven't been disturbed, will remain their service batch, but update the service start time to better one if possibly. And what's more, we have different strategies to choosing the original vessels and the target positions when disturb the sequences. First of all, the original vessels to be moved or swapped are chosen sequentially through the original sequence. We have tried randomly choosing, but it works. And on the other hand, theoretically, every position can be tried to accept moving vessels in the target sequence, but it could be a large number of tests. Thus, we have also tried to test the positions right before the service triggers in the target sequence. And in VND process, the solution with better evaluation will be accepted. On the other hand, due to the sequential optimization processed among the 5 sequences, the sequences are updated group by group, actually, which will cause partially updating with respect to the whole solution made up by the 5 sequences. So how should we evaluate a partially updated solution? We have 2 strategies. Number one, we just evaluated the whole solution systematically. And number 2, we can just evaluate the decompose the group updated sequences belong to. The first strategy leads to so-called systematic VND, and the second one leads to decompose the VND. And finally, for the dynamic situation, we have proposed the rolling horizon scheduling algorithm. In this algorithm, a time window with fixed length is set to fill a segment of the within each sequence, in which every vessel will arrive before the end of the time window. And further, the segment will be cut down to a limitation number of vessels, and then the VND search process will be carried out for this cut down sequence segment, and then the time window will be rolled further to the end of the current time window. Above all, we have made some experiments that are motivated by these 2 questions. Actually, the data of experiments simulation. I think that the simulation lockage traffic generated by the 4 kinds of flow distribution, multiple the 6 kinds of the vessel's size distribution, and that for the first question, we have tried 4 combined strategies in VND search for optimizing the temporal evaluation. The strategy SA means systematic VND with testing or position in target sequence, and ST means systematic VND with testing only right before safety triggers in target visits, and so on, DA and DT. When we set C equals 0 in the EW, means that we just considering the temporal evaluation, and the result can be obtained that the best relative improvement among the strategy between 0.565 to 0.834 depends on traffic density, and 60.7 of all cases got best evaluation when employing the strategy SA, and while all the other cases got best when employing strategy DT. Regarding that, SA creating the largest neighborhood, while DT creating the smallest one. So we can say the strategy DT is good enough for optimizing temporal evaluation. And for the second question, we have tried 4 guiding evaluation special evaluation in VND search. The result shows that in 70.7 of all cases, the best ZU was obtained by employing guiding evaluation ZB, and in 21.4% of all cases, the best ZU was obtained when employing guiding evaluation ZG, and in 70.9% of all the cases, the best ZU was obtained when employing ZF as guiding evaluation. But we can say that from this picture, we can say that the case employing ZG as guiding evaluation converted much faster than those employing ZB and ZF. Thus, all the guiding evaluation can help to search better sequence with respect to spatial evaluation than the raw evaluation ZU. But ZG that designed by us here is more suitable for time-sensitive missions. And for the third question, we've tried a rolling horizon algorithm with 2, 4, 6, 8 hours time window. And we have compared with the long-term static algorithm, and the result can be shown in this table. And the result shows that the rolling horizon algorithm performed better for temporal evaluation optimization, and the 6 hour time window is more suitable for the situation where temporal evaluation and the spatial evaluation are both concerned. Finally, for the last question, we have tried cases that set C between 0 and 1 in W. That the value of C can represent how important of spatial optimization in the scheduling. As shown in this table, what's interesting is that as the spatial evaluation is blended in, increasingly, the temporal evaluation shows a trend of improving within a certain threshold of C. It seems that the spatial optimization gives positive help to the temporal optimization during the heuristic VND search, and the help keeps longer as the traffic is denser, but not always help. Above all, some further questions we need to research listed here. One, we need more efficient algorithm for serving sequence. And two, we need to considering the traffic controlling between two dams. And finally, we are looking for strategic learning for ordering changing in dynamic arrival situation. And so that's all we have. Thank you. And any questions?
Thank you. So
thank you.
I'm a bit late, but it's my fault. So anyone?
Okay.
You can raise your hand if you have a question. Okay. I've got two small questions. The first one is I'm not very familiar with those batch scheduling problems. If you remove the packing aspect of your problem, is it an easy problem or is it already hard?
Sorry?
Okay, sorry. If you disregard the packing constraints, just the scheduling part of your problem, you want to minimize the flow time.
Yeah.
And is it an easy problem or a hard problem? If you don't have the packing constraints.
It's a hard problem. Yeah. It's
already hard.
I've concerned the packing constraints here.
Okay, sorry, I wasn't sure. So if you remove the packing constraints, does the problem get easy or is it still hard?
Maybe here.
Yeah.
Yeah.
Okay, never mind. I see there's another question from Antonio. You want to ask your question, Antonio?
Yes, thank you. No, it was, I just, can you hear me, Tom?
Yep.
Yes,
yeah,
yes, good.
Okay, so
yeah,
no, it was a nice presentation, comprehensive number of strategies for the VND.
Thank you.
I was thinking, and then you have the rolling horizon. I was thinking if you managed to some sort of assess or compare the results that you obtain versus perhaps some real data.
Yeah, we just sample from real data. Yeah.
So you managed to compare with what they are currently doing as well. Perhaps I missed that. But
unfortunately, it's hard to compare with the real situation because you know the real situation is just very bad now because the scheduling is made by the manually. So we just research how to use it, the automatic algorithm to deal with it.
Okay. Okay, thank you.
Okay, thank you.
Okay, so since we are already a bit late, we'll.
Sorry.
No, it's my fault again. So we'll switch to the second presentation right now.
Okay.
Okay, so you can stop sharing your screen. Can you stop sharing? Yes, thank you.
Yeah, I've stopped.
So the second presentation will be given by Nicolas Assis.
Yes, I will share my screen.
Okay, we can hear you and we can see you, so. You can start your presentation. Yep, we can see you. Perfect. So you can start your presentation now.
So, hi, I'm Nicolas, a PhD student at Unesp in São José do Rio Preto, and my supervisor is Socorro. Our work is entitled Heuristics based on dynamic programming for the two-dimensional cutting problem. And this research is supported by FAPESP and CAPS. So our objective of study is the constrained two-dimensional guillotine cutting problem. So there is a large object that should be cut into smaller items, and we do not cut more items than necessary. Furthermore, given the restrictions of the cutting machine, only the guillotine cutting pattern in two stages are allowed, like this pattern, and not this. This problem is part of the production planning process in many industries. In this picture, we can see a furniture industry that has large wood boards that will be cut into smaller boards for furniture production, like this figure. This is an example of a piece of furniture and the associated items. Many authors have studied this problem. This table shows the ones that are more related to this presentation. The first two authors address the unconstrained case. Montgomery proposed the two-step method that is the basis to our heuristic. And a similar approach is given in Fayard, who also use Montgomery's method, and also ideas presented in Bunt. And this problem is still of interest, as can be seen in Velasco y Uchoa and Martin et al. we propose adaptation of the two-step Gilbert-Gomez method for the constrained case. In the step 1, M knapsack problems are solved to obtain the strips that will be combined in step 2 to obtain a cutting pattern. So the first multiplication is to add upper bounds for the variables, this variable ki, that represents the number of items I in strip k in the first M knapsack problems. Also, it is necessary to add a set of constraints to the knapsack problem, this constraint 2.3, that's solved in the step 2. And beta k represents the frequency of strip k in the cutting pattern. The first M knapsack problems are solved simultaneously via dynamic programming, in which stage K and stage C we solve the optimization problem 1. This problem is solved by adaptation of Perrin and Rangel algorithm and the Horowitz and Sani algorithm. And we call it as algorithm 1. It uses ternaries T, like this expression 2, in which the first coordinate is the capacity of the knapsack, the second, the value of the knapsack in stage C of stage K, obtaining by expression 3, and the third coordinate is the frequency of item K in stage C of stage K. We also use a dominance relation between the ternaries stated as stated in expression 4. The ternary T bar is dominated by the ternary T if C is less than or equal to C bar and Z is greater than or equal to Z bar. So the algorithm 1 is given as follows. We will construct the sequence of ternaries that are increasing order of the first coordinate, feasible and non-dominated. First, we construct the sequence S1, which term in S1 is obtained by the multiplication of J with the ternary that represents item 1, with J varying in J1. And the set J1 determines the feasible frequency of the item 1. And the other SK sequence with K greater than or equal to 2 are constructed by recursion as follows. First, we construct the intermediate sequence SKJs. So SK0 is equal to SK minus 1 with the third coordinate of all ternaries equal to 0. So it represents the solutions in which the frequency of the item K is 0. Then SK1 is obtained by adding LKPK1 to all the ternaries in SK0. SK2 is obtained by adding 2 LKPK1 to all the ternaries in SK0, and so on. And the general form is given by expression 5, remembering that the set JK will control the frequency of item K in the knapsack. After obtaining all SKJs, we do a merge process, which is the ordered, feasible, and non-dominated union of all SKJs. So the ternaries are organized in increasing order of capacity. The infeasible ternaries are eliminated. And finally, the dominated ternaries are eliminated. So the problem is solved at the end of the construction of our SKs, and the final solution is obtained through a recovery process. To solve the last knapsack problem, step 2, we developed a relaxation heuristic, and it works as follows. We built a relaxation of the knapsack problem by removing the constraints 2.3. These constraints are used to compute simple upper bounds for the variables beta k. The bounded knapsack problem is solved using algorithm 1. And finally, a feasibility process is then applied for the solution of the knapsack problem. So giving more details of the heuristic, the new upper bounds for the variables beta k are obtaining in the following way. We take the set of constraints 2.3, which form this triangular system of inequalities, and consider that only the column k has non-zero coefficients. And with this, the system will look like this. Then by doing manipulations, we obtain a upper bound for the strip k in the cutting pattern. So the set jk necessary in algorithm 1 is given by expression 6. And this process is repeated for all k, ranging for 1 to m. Given the new upper bounds, we relax the last knapsack problem, transforming it to a bounded knapsack problem, and use algorithm 1 to solve it. With algorithm 1, we are able to recover m cutting patterns, and then the feasibility process is applied on each one of them. And the feasibility process is quite simple. It removes the item in excess from the cutting pattern. For example, in this figure, the maximum number of the beige item is 5. So here, one beige item has been removed from the cutting pattern. The first computational tests were executed using a computer with a Core i7 processor, 3.12 gigahertz CPU, 16 gigabytes of memory, and 64-bit Windows 10 operating system. The algorithms were coded using the Julia programming language and the JUMP modeling language. The instance used have the optimal solutions known and are available in our benchmark, one in 1983, and our library. Their characteristics are given in the table, and the largest instance has object size 1000 by 1000 and 50 distinct items. We compare two strategies to solve the optimization problems in the method. Both uses algorithm 1 to solve the optimization problems in step 1. The difference is in step 2. In the strategy 1 named PC-PG simplex, the last optimization problem is solved directly by the simplex solver. And in this strategy, PC-PGH, it is solved by the relaxation heuristic. From the results shown in this table, we can see that with both strategies found the optimal solutions for the majority of instances, 12 out of 18 instances, and the computational times were all less than 1 second. And one scenario that we could notice happening is the heuristics is this. Suppose the acknowledged strips were created in step 1 of the method. In addition, there is a strip, optimal or not, that's very attractive. So since the heuristic does not fully control the frequency of the strip and the cut pattern, when this scenario happens, the heuristic ends up placing that same attractive strip many times. And when it gets to the feasibility process, it is necessary to remove many items from the cutting pattern. We can see that this happens in the 3 instances highlighted in red, this, and this. When the original problem is solved, it is possible to choose the best strips to compose the optimal cutting pattern. And the other instance that not found an optimal solution is because the optimal strips were not created at the step 1 of the method. So as future research, we solving new instance generated by 2D backgen, an instance generator presented on Silva et al. 2014. Then we intend to explore the strategies proposed in one and fired strategy of using vertical and horizontal strips to compose a cutting pattern. Also to implement item rotation in algorithm 1 and get new upper bounds for the frequency of strips in the cutting pattern so that the highlighted scenario does not happen. And finally, we intend to study the cutting problem and the cutting stock problem from the multi-objective point of view. So these were the reference used, and thank you.
Okay. Thank you very much for your talk. So we have 1 or 2 minutes for questions. So again, raise your hand if you've got a question. Maybe I've got a small question. I can see that the instances you use are not that big. Did you compare your results with an exact solver?
Yes.
I mean, two-stage guillotine for 50 items. I think it's not that difficult.
Yes, we will solve more instances in the next phase of our research. Yeah, this instance, not large instance. So it's the first step to our research.
Okay, and because you use techniques based on dynamic programming, and here I can see that the size of the stock length is not, L is equal to 1000. It's not that large. If you take very large instances, maybe your dynamic program will have a hard time solving those, even the 1D problems. What do you think?
Yeah, we still study this, read the the papers, it is something that was related. If the size of the problem was very large, it's possible the dynamic problem have a difficulty to solve the problem.
Okay, thank you. So maybe a last question. Oh, okay. So thank you again for your talk. So we'll switch to the last presentation. I think Mauro Rosso will talk.
Oh, yes. Can you see my screen? Can you hear me?
Yeah, I can hear you. I can see your screen and I can see you. So everything is.
Sorry, just that is a problem.
So cannot see your slides anymore. Oh.
Oh, yeah. Right, okay. Okay, so I guess you can see it now. Okay. Okay, great.
Right.
So this presentation deals with dynamic programming algorithms for two-dimensional cutting problems. The work comes from the research activity of Ops Lab optimization and problem solving at the University of Naples with colleagues MASONE, SFORZA, and STERLE, and with my contribute from Hitachi Rail in Naples. Well, I'll briefly define the problem and give some hints about literature. Then I'll discuss 3 points: the proposed dynamic programming improvements, the parallelization for CPU multicores, and the integration with new bounds. Finally, I will give preliminary results. Please note that for the sake of time, I'll not describe in details some formulas during the presentation, but you can ask me at the end. As you know, even from previous presentation, we have a rectangular item sheet from which each one characterized by its size and profit. However, we have no limits on the number of pieces. As constraints, pieces cannot be rotated, and only guillotine cuts are accepted. The objective is to maximize the total profit of extracted pieces. About literature, we have here the main contributes related to dynamic programming, but we do not discuss our results obtained in 2014, after which there is the contribute of Boschetti with a massive parallelization on GPU. So for dynamic programming, I remind you that the knapsack function is the best profit for each couple of coordinates. It is recursively defined as the maximum among 3 terms: 1 for the case of a single piece, 1 for the case of vertical dissection, and 1 with horizontal dissection. So if you look at this grid of coordinates and consider the value for the coordinates of the black point, it can be combined with the 2 points in red. The one on the left will affect the vertical term on the blue point, whereas the one below affects the horizontal term on the green point. The support functions that are even very important, lambda and omega, are instead defined as the minimum cut coordinate corresponding to the best value. For example, if the best case is with a vertical cut, we have lambda equal to x and omega equal to w. The opposite in case of a horizontal cut, or both x and y when both directions produce the best value. A special case with value 0 occurs when the best value is not better with respect to lower dimensions. Gilmore and Gomery defined 3 conditions against redundancies. For example, for the vertical term, they avoid a sum if omega is 0 for x1, but they accept if this happens for x2. However, Hertz found that this condition affects the optimality. So in our previous work, we demonstrated that a correct condition is C1, requiring that both omega values are 0. But a drawback is the need to apply a check for each combination. Moreover, in our last work, we defined a proper array of values satisfying second and third conditions. So what we propose now is a way to use this array of values to support the condition C1. On the head of this array, we store the values that satisfy also the condition on omega. On the tail, we store the values that do not. So we even do not increase the need of memory. In this way, we need only one check to decide if beyond the head values, we have also to use the tail values, and we reach the minimum effort, the maximum effect with the minimum effort. Okay, let's move now to the parallelization. Well, we divide the grid of coordinates in rectangular blocks. First, one thread will process the pink block, for example. Then two threads can process in parallel the two blue blocks. And then the green blocks, and so on with several diagonals up to the top right corner. Note that when the pink block, two blue blocks. At the same way, when the two blue blocks are processed, there is an effect on the green blocks. So there is a contemporary effect on the central green block when the two blue blocks are processed. But really, there is no need of mutual exclusion, as in vertical direction, the horizontal term is affected, whereas in horizontal direction, the effect is on the vertical term. I want even underline that our goal is not a massive parallelization. We just want to exploit the multi-core feature used by the CPU suppliers to improve performance. Boschet instead exploited a different scheme for GPU. In practice, in that approach, each thread computes a single sum, and then comparisons are made in parallel. So we do not intend to compare versus GPU. But note that CPU has less memory limits, and indeed we could solve even bigger instances. So let's move to the bounds. The NAPSA function actually represents a grid of upper bounds to be used for the problem with the limited number of pieces. In practice, the problem that our colleague presented before. But if we do not need this feature, then we can integrate dynamic programming with bounds. And the trick is that when the bounds lead to prune a node, we set both lambda and omega to 0. Moreover, as you know, using bounds can ideally determine even a superlinear effect over the number of threads. Finally, better bounds can improve the preprocessing that is aimed to remove some pieces. So we use 3 new lower bounds. The first one is inspired by GPSC of Fayard, as our colleague reminded before. It is based on dynamic programming to find good strips of pieces and then combine them on the opposite direction. The final solution, however, has 2 parts, where on each side different directions can be used. So what we do with respect to this bound, we apply an improvement through stack of pieces. As you could see, we add 2 small green pieces, for example. But we also apply some simplification with time to reduce memory needs and computation time, even at the cost to obtain smaller values. For inner nodes, we try 2 dissections of the complementary area, and then we fill each part with strips combinations, exactly as in the root node. The second lower bound comes instead from an empirical consideration on the structure of the solution for difficult instances. we can see that each of them has a big part made by a very simple structure with just one or two piece types. Note that the pictures here do not report the distances in an exact scale, and the real gap is often small on each direction, sometimes even 1, 2, or 3%. The same happens even for instances that are more difficult. For example, the one on the right takes more than 3 hours with our previous algorithm. Well, about the further lower bound, the idea behind it is to use first only big pieces. This is because after the preprocessing, they probably have a higher ratio between profit and area. And then by using only big pieces, the complexity of the problem is much smaller. So we solve the problem with only the big pieces, and then we fill the holes with simple structures of small pieces. About upper bounds, we start from some literature upper bounds, in particular 2 kinds of one-dimensional relaxations. The first uses only the area, but it generally is integrated also the continuous relaxation on piece number. And the final expression is very simple, with best profitability times the available area. Second one uses instead slices of pieces to fill slices of the available area. So we have 3 new upper bounds that improve the ones shown before. Indeed, what we do is to try to recover the limits that can be due to the integer number of pieces. For the sake of time, I'll explain only the first. The idea is to use the best profitability only up to the maximum area that can be filled by the corresponding piece type. Then we proceed with the second best type and enlarge corresponding area, and so on up to filling all the available area. About the other 2 bounds, I just say that the same principle is applied even for the upper bounds based on slices. These 2 bounds do not dominate each other. However, for the second kind of upper bounds, we obtained even a better way to use the involved types, so leading to the 5th new bounds. So let's finally discuss preliminary results. We use the same instances of our previous work. We also add 12 new extra large instances. And we also consider instances from the work of Boschetti. So I'll show first the impact of the 5th condition improvement, then the effect of adding parallelization, and finally the results of bounds integration, but actually only the 1st lower and the 1st upper bound. So we compare our previous algorithm with the new one, running both of them on the same hardware. On these unweighted instances, we have a speed up that is between 1 and 1.6, but really in one case, there are similar results for the other unweighted instances from Boschetti. However, in this case, the speed up is a bit smaller. For weighted instances, instead, the speed up is sometimes around 2. We note also that looking, for example, at the computation time for LW1, we can say that the new hardware is about twice faster than the old one used in 2014. Indeed, the computation time was around 30 seconds. We use this consideration in a moment. Now let's see the parallelization for 3 groups of instances. For the LW instances, the speed up is up to 3 over 10 threads, but also 3.5 and 4 for 3 instances. For LU instances, the speed up is even better, generally up to 4 or even more than 4.5. Similar results for LX instances. In this case, we have around 3.5 and almost 4.5 for the LX7. Let's see now the impact of both parallelization and bounds. The speed up of the parallelization can reach even values as 7 or 8. Note that we also overcome the results of GPU parallelization, but the factor that we can see about 2 or 3 is probably due to the new hardware generation that we used, as I mentioned before. However, for example, for the instance testcat 7500, we are about 18 times faster. About instead the impact of the bounds integration, it seems that computation time is generally the same, sometimes a bit worse, sometimes a bit better, but in some cases there is a good improvement, even 6 times better. On these other instances, the comparison shows similar results. In some cases, the bounds allow to find the solution at the root node, so we have a good further speed up. Here again, similar results. Here we have the special case of LU4 solved at the root node, but also the worsening for LX5. So we can summarize the results by groups of instances. We can see that in average, the speed up factor is between 4 and 7. However, for the biggest instances, the computation time is still high. Nevertheless, for those big instances, we can note that the gap between a root lower bound and the optimum is very small, up to 7 orders of magnitude less, while the computation time to obtain it is low. Let me finally show the scheme of a couple of LU integrate solutions. We have on the left case more than 100 blocks of equivalent pieces, whereas on the right case we have more than 700,000 pieces on the right. So to conclude, the new algorithm is up to 10 times faster, and we solved new instances. We reached the same performance of a GPU parallelization. However, we are still working for an optimal tuning of the strategies, and we have to fully integrate even the other bounds. Okay, thank you. I ended my presentation if there are questions.
Okay, thank you very much for your presentation. Are there any questions?
I will stop sharing.
Or maybe you can keep your slides so we can, if someone has a question.
Okay. It's just to see you on the screen. If I share...
okay, you cannot see.
Okay, now I can see you.
Okay. Okay. Why? Okay, I will leave some time to raise your hands. I have a very small question. When it comes to parallel optimization, load balancing may be an issue. When you've got bounds, probably you cut a lot of nodes or states in some part of your graph, and somehow all the work is in the same nodes, and some are waiting a lot for the others to finish that job. So maybe that's the reason why the lower bounds and parallelization do not work that much together. What is your feeling?
Our opinion is that I even told in a slide that using upper bounds and lower bounds, we expect even an improvement of the improvement over the number of threads. As you know, we could ideally even obtain superlinear improvement over the number of threads. However, basically we have sublinear because of course CPU do not have a real massive parallelization in accessing to the memory. You know, maybe you have dual channels You have cache memory for each core, but it's not a real massive parallelization. Nevertheless, we are still studying the effect of the bounds. As I told you, we show the results by integrating only the first lower bound, only in the root node, and then only the first upper bound. So we are trying to understand how much your considerations are true or not. Even I can say that in some instances, we saw that the number of nodes in which the upper bounds helped to cut that node was not so big compared to the overall number of nodes. But it's like in some way, I mean, this happened even for instances where the improvement is very good, twice or 5 times faster. And our feeling is that those few nodes in turn determine a reduction on the number of combinations that we use later in other nodes due to the anti-redundancy conditions of Gilmore and Gomoly. So let's say that is the combination of all strategies that is able to reach those results.
Okay,
but the research is still in progress. Thank you very much for the question.
Okay, thank you. So any other question? Okay. Anyway, we are already a bit late, so maybe we can conclude this this session. And so we have a 15-minute break. Am I right?
I think if we can take a bit less than 15 minutes, the next session's due to start at past, but as it's maybe we can start just 5 minutes later to give people a little bit more break. So back at 25 to.
Okay.
Okay.
Let's do that. Thank you.